So this is when you have a closed interval. Now, the issue is, we're in 3 dimensions now, so you could have closed intervals in multiple different aspects. So it's not just, in terms of x. We have it also in terms of y. So what we have to do is account for the fact that, yeah, maybe there's a lower high point on, or critical values associated with a function over an interval, but maybe it's not the lowest point overall. All right, so that's what we have to look at here. But it starts the same way, which is good news. Much simpler function. So 2x minus 2 would be my first partial, my first order partial with respect to x. My first order partial with respect to y would be 2y minus 6. Set them equal to 0. You get x equals 1, y equals 3. Now, this is not a case where you have first order partials that are made up in terms of multiple variables. So our critical value here would be 1, 3. So now we could actually figure that out just by plugging and chugging. Because this is actually more of a numerical approach anyway. So we're looking at 1 squared plus 3 squared, that'll give me a 10, minus 2 times 1, so 8, minus 18, so negative 10, so 4. So 1, 3, 4. All right, so the question would be, based on the diagram, it looks like, okay, if there is a critical value here, it's most likely related to what it would appear to be a minimum, but we have these constraints and it's really hard to tell. Right? We don't know if this is actually coming back up as it goes towards the lip or if it's actually smoothing out. We're not really sure. But what we can do is test the boundaries and see where this is going to end up going. All right, so the number to beat is 4. All right, so the way we're going to handle this is by testing those boundaries. So I'm going to look at x equals negative 2. I'm going to follow the path of x equals negative 2, which means I'm going to actually substitute in a negative 2 to the original function and see what that gives me. So we're looking at negative 2 squared plus y squared minus 2 times negative 2 minus 6y plus 14. So it cleans up to y squared minus 6y plus 14.
That's a plus 4. Negative 2 times negative 2 is plus 4.
What am I
Y
looking at?
squared minus 2 times negative 2.
Y squared. Oh, plus 4. Oh, thank you. So y squared minus 6y plus 22. Okay, so this is the equation of a parabola that opens upward. Right, so let's put this in standard form or vertex form. By completing the square. because it's probably the easiest approach. If I want to complete the perfect square trinomial here, what number would go in the gap?
Plus 9.
+9. All right, the b value cut in half and squared, right?
Minus 9.
-9?
Plus 9, plus 9.
+9, +9, -9, yeah. So so this whole part here becomes y minus 3 squared plus 13. All right, so this would have a vertex at 3, 13. All right, but really you got to think about context here. This is an equation that's defined for z in terms of y. All right, so we have a y value that gives a z value as a result. All right, so what we've established is that we have a parabola that would open upward with a low value of 13. All right, so that's telling me that the 4 is already the lowest value compared to this number. All right, so 4. Because the a value is positive.
So we know that the 4 is the lowest number you said?
We know compared to this number, yeah. Because if this point, this definite point has a z value of 4, this one has a z value of 13 and can go no lower. Because that's the turning point of the parabola and it has to only go up from there. Then it could never get as low as the 4.
But now because that's the minimum boundary, does that mean that we know for sure that 4 is the lowest? 4, no.
So now we test x equals +2.
So what?
And then y equals 0. And then y equals +4.
We have to test both ends.
All 4 boundaries. Oops. So 2 squared plus y squared minus 2 times 2 minus 6y plus 14. It's the one I was expecting before, I think.
Yep.
Y squared minus 6y plus 14.
And now we know it's still
Plus 9 minus 9. Vertex 3, 5. And opening up. All right, so far 4 is winning. We just have 2 more calculations to do. One of them should be pretty easy.
When you say that, what do you mean 4 is winning?
Since we're looking, since 4 is a critical value, we know it's either the minimum or the maximum.
Oh, okay.
Since 13 is higher than the 4, we knew it wasn't going to be the max. So far it's in the lead for being the minimum.
Okay.
It is still possible that it could be a saddle point. If we get a number that ends up being smaller than 4, then that's what we would conclude on this particular interval. All right, so y equals 0. So f of x comma 0. So x squared, all the y stuff cancels out, which is great news. So minus 2x plus 14. X squared minus 2x plus 1 minus 1.
Do they usually have the same z?
Not always, just this type of function because this is a quadric surface. It has some symmetry. So this vertex is 113, but this is comparing, because it's z in terms of x, this is comparing x and z. All right, but it's still a z value. All right, and that z value is still not as low as 4. All right, so 4 is definitely winning the race here. Definitely winning. All right, and then finally, the upper bound, which is, I believe, y is 4. So x squared plus 16 minus 2x minus 24 plus 14. So x squared minus 2x, and then we have 16 minus 24 is what, negative 8? So 6. So it's still plus 1 minus 1. X minus 1 squared plus 5. So same deal as the other bound. Vertex 1 comma 5. But it goes as low as 5, but no, it doesn't quite get to the 4. All right, so therefore 4 is the minimum value. On the closed interval.
So would we write that to answer the problem, a critical point 1 comma is the absolute minimum?
The absolute minimum would be 4.
Oh,
Yeah, because it's the z value that represents, just like in the xy plane, it's whatever the y value is that represents the absolute max or min.
Okay.
In this case, it's the z.